Alright, just a comment about that homework I gave earlier for the Carnot cycle. Okay, just to help you out in your derivation. Remember, you have two isotherms, T hot and T cold, right? And you have 4 points there that are part of your cycle. So you have adiabats crossing your isotherms, reversible adiabats. So this is pressure, volume. So this one is P1, V1, T hot, and that point right there, and that point right there is P2, V2, T hot, and that point right there is P3, V3, T cold, and this point over here is P4, V4, T cold, right? So, like I said, you need the expression for Q and W for each step. So remember, the steps are what? A is reversible isothermal, B is reversible adiabatic expansion, and then C would be reversible isothermal compression, and then D would be the reversible adiabatic compression. Okay, so you need an expression for Q and W for each one. Q should be easy for the adiabatic, right? So if you have an isothermal, what would be your Q and W? You know delta U is 0 since it's an ideal gas. The formula for W was negative nRT ln V final over V initial, right? And your formula for Q is just positive W, right? Since Q and W should add up to 0. And then for the adiabatic steps, okay, you know that your Q is going to be 0 because it's adiabatic. So your delta U is just going to be equal to W, and that's just going to be CV delta T. So T hot minus T cold, or CV T cold minus T hot, depending on whether you are doing process B or process D. Okay, so it's just really CV delta T. Okay, so let's just make this generic. It's just going to make it CV times T final minus T initial. Okay, so you'll have formulas for all of those. And what was it you wanted to? I wanted you to show. The efficiency is equal to T hot minus T cold over T hot, right? And one useful thing that you need to do first is you need to first show, this is going to be very important, that V2 over V1 is equal to V3 over V4. Okay? And you can base that on the adiabat. So in other words, this V2 right here over V1 is equal to V3 over V4. And you can show that based on the fact that the reversible adiabat is TV to the gamma minus 1 is a constant. Okay? I want you to express T hot over, or T cold over T hot here. Here's a hint for you. T hot over T cold, express that as a ratio of volume to the gamma minus 1. You do that for the two adiabats, and you should be able to show that V2 over V1 equals V3 over V4. So you derive this expression for the two adiabats that you have for process B right here and process D. And that should help you out in deriving that final formula. Okay? And remember, what was the formula for efficiency? That was total W, right? Divided by negative total W over Q in. which is Q for process A. This is Qn is Q sub A. And we should be able to show by doing this that you'll get T hot minus T cold over T hot. That's your efficiency. Alright, so let's pick up where we left off last time. Isothermal phase changes, like I said, there's an empirical rule. Empirical simply means what? It's based on experimental data that you can use to estimate delta S. It's not perfectly accurate, but it's reasonably accurate for a lot of gases, especially nonpolar compounds made of nonpolar molecules. Delta S vaporization is about 88 joules per Kelvin per mole. Okay, so let's estimate the enthalpy of vaporization of a liquid that boils at 78 degrees. Well, delta S at constant temperature and pressure is just equal to delta H at constant temperature and pressure divided by T. So what's the delta H vaporization? How do I solve for delta H vaporization? Delta H vaporization at constant temperature and pressure is approximately equal to T times delta S. It's equal to, not approximately equal to. It's equal to T times delta S at constant temperature and pressure. What's our temperature? Right here, 78 degrees. Right. So 78 plus 273 Kelvin. Oops. That's in Kelvin. Times our delta S. Approximately, what's our delta S? 88 joules per Kelvin per mole. Okay. So what is 78 plus 273 times 88? $30,888 joules. And so Kelvin cancels out, right? So that's just going to be joules per mole. So that's equal to 30.9 kilojoules per mole. Okay, so that would be 31 kilojoules per mole. Since we only have two sig figs there, really, so it's 31 kilojoules per mole. 31 kilojoules. All right. Isothermal expansion or compression of a gas. Let's recall what the formula is for isothermal expansion of an ideal gas or compression. What's delta U? Ideal gas, 0, right? Isothermal, ideal gas, delta U is 0. So delta U is Q plus W. So Q must be equal to negative W. And what was our W? Negative integral of P dV, right? So that's going to be negative integral of nRT over V dV. So you pull out your nR. Okay. So that's going to be negative nRT. Pull out the T. ln V2 over V1. Okay. So our Q, which is negative W, would be negative, negative, so that's a positive now. RT ln V final over V initial. This is per mole, so our N is 1. Okay? Or it can also be equal to negative RT ln PI over PF. You remember why that is? Okay, so W is negative RT ln V final over V initial. Since it's isothermal, then PI VI is equal to PF VF, right? So that's the same thing as negative RT ln pi over pf. Okay, so that's your formula for Q. This one right here. And that's going to be negative W. So delta S for an isothermal expansion or compression of an ideal gas is just Q over T. Why? Integral of dQ over T, that's your delta S, right? It's isothermal. I can pull my temperature out of my integral. It's a constant. So it's just going to be integral of dQ times divided by T. That's just Q at constant temperature over T. Okay? So it's just going to be what happens if you divide. What happens if you divide this by T? You just lose that T, right? So the delta S is just equal to R ln V2 over V1. Okay? Let's get a sense of what this means. What happens if a gas expands? What is Vf over Vi if a gas expands? Less than 1, greater than 1? If it expands. Greater than 1. What's the natural log of a number larger than 1? Positive or negative? It's equal to a positive number. So if it's expansion, delta S is positive. Okay? So it's positive. So isothermal expansion leads to an increase in entropy. What if the process is irreversible? It doesn't matter. As long as you know what your initial state and your final state is, you can always imagine the process happening reversibly. In fact, you have to imagine a reversible process if you want to calculate delta S. So, like I said, calculating delta S requires that you identify initial state, identify final state. It doesn't matter how it happened, just imagine a way to get from your initial state to your final state. And just integrate dq over t for that process that you imagine. That process that you imagine must be reversible. Okay? That's why we're building up our arsenal of formulas here for the different types of processes, so we can link them up together to imagine any sequence of processes for whatever it is we might be interested in. Okay? Here's an example. You have an ideal gas initially on 1 bar, undergoes an irreversible isothermal expansion against a constant external pressure of 0.1 bar. Let's calculate delta U, Q, W, delta H, and delta S. All right, so delta U is 0. Why is delta U 0? We know that because we're dealing with ideal gas isothermal. So Q must be equal to negative W. Why is that? Because if delta U is 0, then Q plus W must be equal to 0. So Q is equal to negative W. What's the formula for W? It's negative integral of P external dV. So why is that just equal to negative P external delta V? Because your external pressure is constant, so I can pull that out of my integral, right? So that's just going to be equal to negative P external V final minus V initial. So there's a formula for W, Q and W and delta U. Okay? Do we have any information to calculate? I'm sorry. Ooh, that's right. Thank you. So that should be negative, negative. Yeah, so that should be positive. Thank you. So that's plus positive P external V final minus V initial. Okay. What about, okay, do we have enough information to actually calculate W and Q? We don't know because we don't know what the final volume is, what the initial volume is, right? But do we know delta H? Why is delta H equal to 0? Isothermal, ideal gas. Delta H is 0. We've shown that earlier, right? Delta H and delta U is 0. It's isothermal and ideal gas. How do we calculate delta S? Well, delta S is just going to be, you just imagine a reversible path that goes from whatever V1, V initial you have to whatever V final you have, right? Isothermal, reversible. So what would that be? NR ln V2 over V1. Okay? Do we have, can we calculate delta S then? Do we know V2 and V1? Okay. How did I get 19.1? Isothermal, what do we know about V2 over V1? Or VF over VI? Isothermal, ideal gas, that means PI VI equals PF VF, right? So if I want to know VF over VI, that would give me what? That's PI over PF. So I can rewrite this as NR ln PI over PF. Do I know what PI and PF is going to be? You went from 1 bar pressure, you suddenly reduce your external pressure to 0.1. So what will be my final pressure? When will it stop expanding? When the final pressure is 0.1. Okay? So you can say this is going to be NR ln, initial pressure is 1 atmosphere, 1 bar, I'm sorry, and final pressure is 0.1 bar. So this is going to be equal to NR ln, what's 1 over 0.1? 10. So what's NR times ln 10? What's R ln 10? $19.1. It's got to be. That's the answer I gave, right? 8.314 times ln of 10 equals 19.1. Okay? So that's 19 N times 19.1 joules per Kelvin per mole. I still don't know the actual answer because I don't know how many moles of gas I have, right? So that's why I just gave you the answer in per mole, on a per mole basis. All right. Now, in general, then, if you're interested in calculating delta S for a change involving an ideal gas, you just go from P1, V1, T1 to P2, V2, T2, okay? So you want to go from P1, V1, T1 to P2, V2, T2. A strategy you can use, let's say this is 1.1 and point number 2. Let's say this is on this isotherm and this one is on that isotherm right here. What you can do is you can take a reversible isobaric change, let it expand, okay, to whatever your desired final volume is, and then you go isochoric, right? That's one way. You just have to determine the temperature for this intermediate point right here. Let's call this point X. So this is going to be T sub X. This isotherm right here is going to be T sub X. So this is T1, T2. And so the delta S for that would be delta S for step 1. What's delta S for step 1? Isobaric. So this is delta S for an isobaric. So delta S at constant pressure. Pressure here happens to be P1. And then this is delta S for constant volume. The volume here is now going to be V2. Integral of Cp dt over T would be the delta S for step 1 right here. this step right here, integral of Cp dt over T. And this step right here, delta S for that is integral of Cv dt over T. Okay? But you do need to identify that T sub x. How would you know that T sub x? That intermediate temperature. Let's magnify that a little bit. Okay. Let's say that's 1, right? And this is point x. So isobaric there, and then this is your final point right here, point number 2. How do I get T sub x? I know that P1 V1 over T1 equals Px Vx over Tx, right? But what is my Px? Px is P1, right? Same as P1. What is my Vx? The same as V2. And so I can solve for my Tx using P1 V1 over T1 equals P1 V2 over Tx. I can solve for my Tx. Or what's another way I can solve for Tx? I can say that P2 V2 over T2 is equal to Px Vx over Tx. So that's going to be P1 V2 over Tx. Remember, for an ideal combined gas law, right? PV over T is a constant for an ideal gas. So either way, you can solve for your Tx. So you solve for Tx first. Okay, identify your Tx first, and then you can do an isobaric and then an isochoric reversible process, a sequence of those two processes, and add up the delta S for each one of those. Here's a simpler approach. Instead of going isobaric and then isochoric, you do isothermal first. Okay? You let your gas expand or contract, change your volume at constant temperature. And once you've changed your volume, all you have to do now is change your, so your volume has changed, right? Okay, volume and pressure will both change. I'm sorry, for the first one. Reverse P1 V1 equals P2 V2. Volume and pressure will change so that you get to your desired pressure and volume. Okay? Not to your desired volume. Okay? And then what you do then is you follow it up with a reversible isochoric change, constant volume, change the temperature to your desired temperature. So you find the temperature that you want. Okay? So let's illustrate that. So here's an isotherm at P1, at T1 and T2. Okay, so here's my point number 1, and here's my point number 2. What did we say we do first? You want to change your volume to the final volume. So I want my final volume, this one right here. So I want my intermediate point there, isothermally. Okay, so this is going to be V2 T1, right? This is going to be some intermediate pressure. Let's call that Px V2 T1. Okay, and then I drop my pressure down to, and my temperature down to T2. So this is going to be my final pressure, P2 V2 T2. So I do isothermal and then isochoric. Another way you could have done this is you can go isochoric and then isothermal. But it's the same thing. It gives you the same result. This is an alternate path. Okay. Something like that. So, correction here. This pressure is not going to be P2. This is going to be some intermediate pressure, P sub x. and some intermediate pressure P sub x. But you end up with your final pressure P2, the desired final pressure. Okay? So what happens? What's delta S for the first step? Isothermal. Delta S for this is equal to what? Reversible isothermal expansion of an ideal gas. NR ln V2 over V1, right? What's the delta S for second step? That second step, what's your delta S for that one? That's just going to be integral of CV dt over T, right? Which is going to be CV ln T2 over T1. The nice thing about this approach is you don't have to worry about what that Px is, because your formulas don't involve P. Okay? So your formula is this. For 1 mole of gas, it's R ln V2 over V1. This is the delta S for your isotherm. Okay? For the isothermal expansion or compression. And what's this one? CV ln T2 over T1. This one is your delta S for the isochoric heating or cooling. So this equation right here is very useful. If you know V1 and T1 and V2 and T2 for your ideal gas, that's your delta S for the change. Okay, that's known as a Sackur-Tetrode equation. This is per mole, so what would you have to do if you have n moles? Just multiply the whole thing by n, right? If you have more than 1 mole. Now, what about an adiabatic expansion or compression for an ideal gas? Now, well, if it's reversible adiabatic, then dq for each and every step is going to be 0. So dq over t is going to be 0 for each and every step. Okay, so your delta S is going to be equal to 0. So in other words, if you have an reversible adiabatic process, okay, a reversible adiabatic process, okay, delta S is equal to 0. That is also known as an isentropic process. Why isentropic? What does iso mean? Isothermal, constant temperature. Isobaric, constant pressure. Isentropic, constant entropy. Okay? A reversible adiabatic expansion or compression is an isentropic process. Now, what if the process is not reversible? Then delta S is probably not going to be 0. Okay? It's irreversible. So what you need to do again is identify the initial state and your final state. And then you have several examples of those where you can, depending on what the scenario is, you can identify what your initial state is, what your final state. If you know what V1 and T1 are, and you know what V2 and T2 are, how do you get your delta S? That's your formula. R ln V2 over V1 plus CV ln T2 over T1. It doesn't matter if the process was an irreversible adiabatic process. For as long as you've identified where is your initial state, where is your final state, you can use this formula. Okay? So here's an example. Yeah, let's say you have an irreversible adiabatic expansion of a gas into a vacuum, resulting in doubling of the volume. So let's imagine you have 2 gas bulbs that are identical in size. This is a vacuum, so pressure here is 0, and you have your gas in here. Okay, so you open up that valve, and what happens? Your volume doubles. Doubling of the volume. Since this process is irreversible. Why? It just happens spontaneously, right? You're not letting it expand a little bit at a time. You're letting it expand right away. So Q equals 0, adiabatic, right? So W, why is W 0? It's expanding into a vacuum. External pressure is 0. So W is also equal to 0. So delta U for this process is also 0. Delta T is 0. This is ideal gas. Okay? We've dealt with this earlier this semester. So all of this you should already know. Since temperature is constant, then this process is, we've identified our initial and final state here, right? What's our initial and final state? How are our initial and final state related? T2 is going to be equal to T1, right? We know our temperature is not going to change. And what's our V2 and V1? Double the volume, so V2 over V1 is equal to 2. Right? So this, what we can do then is the delta S for this is the same delta S as a reversible isothermal doubling of the volume, right? That's the process that we imagine. So we imagine doing this reversibly, we should get the same delta S. And so what's our delta S for a reversible isothermal expansion? It's just R ln V2 over V1. Okay? The general formula would be plus CV ln T2 over T1, but this one is just 0, right? Second step, we're not changing temperature. So it's just going to be what? R ln of 2. What's ln of 2? 0.693, right? So 0.693 times R. 0.693 times 8.314 is how much? 5.76 joule per Kelvin. Okay, so that's your delta S. It's just R ln 2 per mole of gas. Okay, if you have a mole of gas. All right, let's talk about delta S for heat flow between two things that are at different temperatures. So let's say A is our system and B is our surroundings. First of all, let's imagine both of these, the system and the surroundings, to be at thermal equilibrium. So there's no, what do we know? If your system and your surroundings are at the same temperature, then heat has no tendency to flow either way, right? So there's no propensity for heat to flow either way. Now, let's imagine, okay, so we've got two things at the same temperature. We know heat's not going to flow. Okay? So now let's imagine them separately. Let's imagine heat actually flowing from A to B or from B to A. Okay? So we're going to imagine a reversible transfer of a small amount of heat, dQ, into A. So we have A and B. Oops, what did I just do? So I'm going to have A here and B. I'm going to imagine that a small amount of heat transfers from B to A. So what's ds for A? It's just equal to dQ over temperature of A, right? Now we imagine the reversible transfer of the same amount, the same small amount of heat out of B. So it's coming out of B. So ds for B would be what? Negative dQ, because it's coming out of B, right? So negative dQ over TB. But TB and TA are the same, right? We're saying we're imagining we have two systems that have the same temperature. So dQ over T, let's just call that. And this is going to be negative dQ over T. What's our total delta? What's our total ds for both, for the A and B? dSA plus dSB is equal to 0. Okay? So for a reversible process, then we say that the ds total is equal to 0. What does it mean when ds is equal to 0? The entropy has no tendency to increase, right? decrease, right? So it's either reach a maximum or a minimum. So a small change, a small flow of heat from one to the other will not result in a change in the entropy. Okay? So that's your condition then. If your system, if your A and B is a system and surroundings, then you can say that ds for the universe would be equal to 0. So this is at equilibrium, at thermal equilibrium. Okay? Heat has no tendency to flow either way. But what happens now if B is hotter than A? So we now have, so this is a different scenario now. We now have our system is A and our surroundings is B, right? So we're going to say that TB is hotter than A. TB is greater than TA. What do we know about this? What do we know is the spontaneous process. The natural tendency is for what? Heat to flow from where to where? What's the direction of heat flow that we expect here? Based on our experience, heat's going to flow from hot to cold, right? So Q is going to flow that way. So let's calculate now delta S for A and delta S for B, assuming a small amount of change. Okay, so we're going to now examine these two things separately. Okay, I'm going to move a little bit of heat into A, dq, and for B, I'm going to take out dq, right, negative dq. So we separate A and B. Look at A and B separately. Imagine a reversible process where a small amount of heat enters A equal to dq, and a small amount of heat, negative dq, a small amount of heat, dq, leaves B. So Q for B would be negative of dq. What the dq's for the two, this A and B, would be opposite of each other, right? So what would happen to our delta S? What would be our ds? ds would be what? ds for A would be dq over TA, and ds for B would be what? Negative dq over TB. What happens if we add these two? dSA plus dSB is equal to 1. dq over TA plus negative dq over TB. What happens there? I can factor out dq, right? 1 over TA minus 1 over TB dq. Okay. That's 1 over TA minus 1 over TB. If TB is larger than TA, remember, B is hotter than A, right? So is this going to be positive or negative? This is a smaller, bigger number. So this one is a smaller number. Big number minus a small number, right? Times dq. So this thing is a positive. So your ds is positive. The total ds, the total entropy change for that reversible transfer, okay, is positive. Okay. So that would be the delta S for the transfer of dq from B to A. So if you transfer dq from B to A, okay, that's an irreversible transfer because we know B is hotter than A, right? But if we want to calculate the delta S, we're not going to use that dq and just divide that by TA and TB, because remember, to calculate delta S, you have to imagine a reversible process. So you have to examine A and B separately. Think of a reversible process where dq went into A and another reversible process where dq went out of B, right? And so when you add the ds for both of those, you get the total ds. Well, what did we just show here? The total entropy change is positive. What that means is what? Did S increase or decrease? For this irreversible process, what happens to your entropy? Increase or decrease? Increases. All right? So this leads us to a statement of the second law of thermodynamics, which is what you are more familiar with. Okay, this is the one that got introduced to you in your earlier courses, which says that for a spontaneous process, that the entropy of the universe increases. Delta S of the universe is positive when a spontaneous process occurs. What do we mean by a spontaneous process? Something that has a natural tendency to occur, what we call irreversible processes. Okay? And so what does that mean? While something is naturally occurring, what's happening to the entropy of the universe? It's increasing. And when something stops, what does that mean? So if I have entropy increasing, what happens when the process stops? That means you've reached equilibrium, right? So when you've reached equilibrium, what happens to my ds? You reach a maximum. Please say the entropy of an isolated system, in this case the universe, reaches a maximum. Okay, so ds equals 0. You get a 0 slope at equilibrium. So this is when equilibrium is established. Okay, so spontaneous process, while a spontaneous process is going on, your entropy will be increasing, and it will reach a maximum. Once it reaches that maximum possible value, it can get under the constraints that you have on the system. Once it's reached that maximum, then you say you've reached equilibrium. Okay, so this is the condition for equilibrium. ds is equal to 0. Any further advancement of the process would not lead to an increase in entropy, so it's not going to happen. So when you have two things, we showed earlier, when you have two things that are at the same temperature, heat's not going to flow either way, because the flow of heat either way would not lead to an increase in entropy. You've reached a maximum in entropy. Okay, so that's the second law of thermodynamics. So from heat engines, we were able to define, from studies of heat engines, we were able to define a new state function. We were able to invent a new state function we called entropy. And the nice thing about that new function that we invented is that entropy gives us a way of predicting whether something is going to happen spontaneously or not. Okay? If something is going to happen spontaneously, then we should be able to calculate the change in the entropy to be positive. Not for the system, but for the system and the surroundings combined, the entire universe. Okay? So keep that in mind. The entropy, when we say the entropy increases during a spontaneous process, we're referring to the entropy of the universe. That's the system and the surroundings. It's possible for the entropy of your system to drop. We say your process is incurring an entropy debt. Okay, that can happen provided it's accompanied by a larger increase in the entropy of the surroundings. So, an increase in entropy for the system doesn't necessarily mean it's going to be spontaneous. It tends to be favored, but what we really want is the entropy for the universe to increase, for us to be able to say that a process is spontaneous. Okay. So here's a quick check of that, see if you got the concept right. For a reversible process, delta S is 5.0 joules per Kelvin. What's delta S for the surroundings? Anytime you're given delta S, always take that to mean just the system. Okay, so Unless otherwise specified, when we say delta S, delta H, delta U, we mean the system. So let's say delta S for the system is 5 joules per Kelvin. If this process is reversible, what's the delta S for the surroundings? Negative 5.0 joules per Kelvin. And what's the total delta S for the universe? It's going to be 0. That's always true for a reversible process. Because what happens in a reversible process? Each step of the way, your system and surroundings are at equilibrium. Okay? System and surroundings are at equilibrium. The system and your surroundings are at equilibrium. How about this one? Spontaneous process, delta S is 5 joules per Kelvin. What's the delta S for the surroundings? Positive or negative? So delta S plus delta S surroundings. I can put delta S surroundings here. What's the condition for it to be spontaneous? Positive, right? So if delta S is 5 joules per Kelvin plus delta S surroundings must be greater than 0, what would be the condition for the delta S surroundings? Delta S surroundings must be greater than what? Greater than negative 5 joules per Kelvin. All right. So what does that mean? If your system entropy increases by 5, your surroundings, the delta S for your surroundings cannot drop by more than 5, right? If it drops by, so it can be anywhere higher than 5, right? Okay. So if it drops more than 5, then the process will not be spontaneous. Delta S surroundings cannot be less than negative 5. So it can't be negative 6, but it can be negative 4, it can be 0, it can be positive, as long as delta S plus delta S surroundings is positive. Melting of ice at 0 degrees Celsius, 1 atmosphere is a reversible process, and delta H of fusion is 6.01 kilojoules per mole. What's the delta S for the system and the surroundings if you melt 1 mole of ice? What's our delta S here? Constant temperature and pressure. You remember the formula? It's Q over T, right? What's Q at constant pressure? This is delta H. So this is delta H at constant temperature and pressure over the temperature. What's the given delta H for the melting of water? Melting of ice? 6.01 kilojoules per mole. 6.01 kilojoules per mole. What's the temperature? What temperature is this happening? 273 Kelvin, room temp 0 degrees Celsius. So that gives you how much? 6.01 times 10 to the third joules divided by.
Like this on the test. You want it in kilojoules or joules?
Doesn't matter.
Doesn't matter.
Unless I specify the unit. If I don't specify the unit, you can give it to me in kilojoules or joules. Usually entropy values, you get nice round numbers if you have joules, if you use joules. And for delta H and delta U, usually those numbers are big, so you use kilojoules for those. What is it? 2.2 times. That can't be. Okay, 22. You have to. This kilo is 10 to the third. Times 10 to the third. Okay, so the answer is how much? 22? 22 joules per Kelvin per mole. Okay. What is delta S for the surroundings? Answer. This is reversible process, so negative 22 joules per Kelvin per mole. What happened here? When you melt, okay, so here's your ice, and your surroundings would just be, let's say, liquid water. The tendency for heat to flow either way is the same. So, provided this is perfectly insulated, there's no other heat flow, then the ice will have no tendency to melt. The liquid water, the ice and the liquid would have equal tendencies to melt or freeze. Okay, they're at equilibrium. But why does ice eventually melt if you have a glass of water with ice in it? They are at equilibrium. Okay. Your liquid water is in contact with the warmer surroundings, so heat's gonna flow out of your liquid water, right? So that heat flow out could lower the temperature, could increase the temperature of your liquid water, and so your ice water. You can imagine that happening, and then your ice and liquid water will no longer be at equilibrium. So you'll have a spontaneous process. Okay. And that's it. All right. What would happen if I had, so I'm surrounding my ice with liquid water here at 0 degrees, okay? So my ice is at 0 degrees Celsius, and my liquid water is also at 0 degrees Celsius. What if my ice is only surrounded by air? Okay. So you have ice here, okay, at 0 degrees Celsius, and then you have air at, let's say, room temperature, 25 degrees Celsius. What do you think is going to be delta S for my surroundings? Wait a minute. We got our signs reversed. That's correct. Okay. What would be my delta S for my surroundings? Is it going to be less than negative 22 or higher than negative 22? What would it be? 6.01 times 10 to the 1. Delta S surroundings, heat has to flow out of the surroundings into the system, right? So Q for the surroundings is going to be negative. So heat will flow from surroundings to system. So Q for the surroundings is going to be negative. Negative 6.01 times 10 to the third joules, okay, per mole, divided by, what's the temperature this time of your surroundings? Instead of dividing by 273, you divide by 298. What would that give you? A smaller negative number, right? Which would be what? It's not going to be negative 22 anymore. Negative how much? Negative 20 joules per Kelvin per mole. So what's our total delta S this time? 22 plus negative 20, positive number, as we expect. Because we expect ice to melt. Okay. Now, what if it's the other way around? If your air was like at negative 5 degrees Celsius, what will happen? So that would be an impossible process. So if you put your ice in a freezer at negative 5 degrees Celsius, it won't melt. If you were to imagine it melting, you get a delta S, which is going to be negative. Total delta S, negative. So a negative delta S would be an impossible process. Okay? So here's a common question that people used to test, teachers used to test if you really understood the concept of entropy, is to say, all right, if you have liquid changing into a solid, you've been taught that liquid is in a more disordered state, right? You've been introduced to the idea of entropy as a measure of disorder, right? So liquid is more disordered. Solid, you have more order. So liquid to solid, what happens? Delta S for that process is going to be positive or negative. Water changing to ice at 0 degrees, for example. Water changing into ice is going to be negative, right? A decrease in entropy. More disorder here, okay? You've learned this from your earlier courses, and you have more order here. More disorder has higher entropy, right? And more order has a lower entropy. Well, it would then say, because delta S is negative, then that's not going to happen. True or false? You know it happens, right? But it's not going to. So what's the problem with that statement? The delta S for this process is negative, therefore it's not going to happen. We don't know about the surroundings. You're only looking at the system. You have to look at the system and the surroundings. When is this going to happen, actually? At low temperatures, right? Why does it happen at low temperatures and not? So why does this happen in the winter but not in the summer? Why does liquid water freeze in the winter but not in the summer? Delta S for the surroundings is what? It's Q over T, right? The colder the surroundings, what happens? Smaller denominator so freezing incurs what we call an entropy debt. Okay? Entropy debt. Because that would have a negative delta S. You need to compensate that with, so if something freezes, it releases heat to the surroundings. So freezing would cause the entropy of the surroundings to increase. So you would expect, okay, delta S surroundings, we expect this to be positive, okay? But how positive is it? It depends on what your temperature is. At low temperature, it becomes even more positive. You have a smaller denominator, you have a bigger delta S. So we say then that freezing is favored at low temperature because at when the surroundings has very low temperature, you can cause the entropy of the surroundings to increase more than if surroundings is at higher temperature. In fact, let's do that. Let's just look at water. Okay, let's just look at our surroundings. Let's say you have 5 joules. Okay, you have a surroundings. Let's say so big. Okay, you put 5 joules in, temperature remains constant. What is delta S for that one? 5 divided by, let's say, 273 Kelvin. And it's so big that the temperature doesn't really change by putting in 5 joules. So 5 joules divided by 273 Kelvin. How much is that? By how much does that entropy increase? 5 divided by 273. 0.018. Okay. Whereas, let's say our surroundings is at room temperature, 298 Kelvin. What's 5 joules over 298 Kelvin? Okay. So you can see the increase in the entropy of the surroundings is not as much when it's a higher temperature. Okay. One analogy I like to use for this is imagine energy as the amount of energy, thermal energy as the amount of money. Okay. So if you're transferring energy, let's imagine that as you're transferring money. And entropy, my analogy for that would be your level of happiness. Okay, so let's say Joe here has $1 million, so he has a lot of energy, high temperature, he's hot, right? And John over here is cold. He's homeless. He's cold out there. So low energy. Okay. So John has low energy. He's cold. He's homeless. Okay. Joe is hot. He's got lots of money, $1 million, right? So now I'm gonna give both of them the same amount of energy. I'm gonna give both of them $100. Okay. John's gonna be much happier than Joe would be with that $100. A higher increase in John's entropy than in Joe's entropy. Okay, because you're comparing the amount of energy to the temperature, which is really a measure of the what's temperature? It's a measure of the thermal energy of your system, right? So the higher the temperature of your system, the higher the temperature of your system, the higher its thermal energy is already. Okay, so it's sort of like a law of diminishing returns type of thing. Something's already rich, it's already got a lot of energy. Its entropy is not going to change much if you add the same amount of energy as opposed to something that doesn't have as much energy to begin with. Okay, so it makes a bigger impact. Heat makes a bigger impact on something that is colder. Just like the same amount of money will make a poor man happier than a rich man. Okay, and so that is entropy. And I think that's it for this lecture.